Okay, let's have the derivation of the general cable theorem. This theorem is applicable only when the loads are vertical. So if there is a load that is oblique or inclined, then this theorem is no longer applicable. For that case, you apply statics in order to completely analyze the situation. But let's have the derivation and concept of the general cable theorem applied only to cables subjected to vertical loads. So let's consider this cable subjected to concentrated loads P1 and P2. These are the elements, and we draw a beam which is of the same horizontal span and subjected to same loadings at the same position of loadings. So if this is a simply supported beam, the loads are the same, P1 and P2, and the distances the same. Then the reaction, let's denote them as R1 and R2 in the beam. And we have here the horizontal component of tension because there is no inclined loading, then the horizontal component of tension at any point in the cable will be the same. So because it is tension, the horizontal component should be directed away from the point of application. So that's it. We will denote the vertical component of reaction at A as V sub A and at D as V sub D. Then we draw this imaginary chord, the line, imaginary line joining the end supports. And this is the horizontal line through point A. And the angle here is theta. So that this is L tangent of theta, the vertical distance between them. And we consider a point anywhere on the cable, let's say point Q, at distance x from the left. So take note that you can analyze this system using the principles of statics. So first you have to, let us say, cut or consider the entire system. You sum up moment about D. Then the unknowns should be H and V sub A. Then if the distance, vertical distance from the horizontal line to point C is known, so you may cut the cable, let's say through BC, then you sum up moment about D involving, then you can set up the equation involving H and V sub A, the unknowns. Then you solve the two equations simultaneously to solve for H and V sub A. The rest of the reactions can be found by statics afterwards. So for the general cable theorem principle, let's continue. So we have a point Q here. Any point on the cable, then the distance from the left from point A is x. So this distance would be x tangent theta, the distance from the horizontal line to the imaginary chord. So that is x tangent theta, and we will call this distance the distance of any point on the cable to the imaginary chord as h sub q. Then this is h sub b, and this is h sub c. So this is the general cable theorem which we are about to prove or to verify. That is the product of the horizontal component of tension and the vertical distance of any point on the cable to the imaginary chord. So h times h sub q is equal to the moment at the same point on the determinate beam q on the beam loaded with the same loadings. So that is h times hq is equal to the moment at this point in this beam here subjected to the same loadings q. So to solve for MQ, it's either you solve for R2, then the moment at point Q is simply R2 times that distance, right? If you cut section containing Q, and you simply sum up moment here, that's the moment at Q. But we will compute the moment at Q based from the reference point, which is the left side, so that these loads are involved in the calculation of moment. But when you solve problems involving cables and you can apply the general cable theorem, you can present the solution in a simpler way. That is, you solve for R2 and take moment about Q. So let's continue. So let's consider the cable first, considering the entire system. So we, by static, summation moment about D equals 0, and considering clockwise positive, so our equation would be V sub A times L minus H times L tangent theta, then minus P1 times the moment arm is B plus C minus P2 times C equals 0. So V sub A times L minus H times L tangent theta equals P1 times B plus C plus P2 times C. Let's call that equation 1. Assuming H sub C is known, so summation moment about C equals 0 and clockwise positive considering forces left of C, then we can set up another equation, V sub A times A plus B minus H times A plus B times tangent theta equals P1 times B plus C. So this equation is V sub A times A plus B minus H times, because this distance is A plus B, then the total vertical distance will be H times A plus B tangent theta, then plus H sub C equals P1 times B plus C, or P1 times B. Then solving these two equations simultaneously, and we can solve the value of VA and H. So let's proceed to the cable theorem. So in general, cut cable CD at Q. So considering all forces to the left of Q, so this is our first equation. So summation moment about Q equals 0, clockwise positive, then we'll have V sub A times X minus H times this total distance is X tangent theta plus HQ, or HQ plus X tangent theta, then minus or equals P1 times X minus A, this distance is X minus A, then plus or minus but transposed to the right, so plus P2 times this distance is X minus quantity A plus B. So call that equation 3. Then V sub A times L minus, this is from equation 1, H times L tangent theta equals supposedly P1 times B plus C plus P2 times C, and we will call this summation of moment about D due to the loads. So this value is P1 times B plus C, then plus P2 times C. So we will just call it summation of moment about point D due to the loads. So call that equation 1, which is the same as this. Then V sub A times X, also summation moment about Q equals 0. So V sub A times X minus H times HQ plus X tangent theta, and equals supposedly P1 times the equation here. So P1 times X minus A plus P2 times quantity X minus A plus B. Then we will call that from equation 3 as summation of moment about point Q due to these two loads P1 and P2. Then considering the beam. So since our objective is to find the moment at Q, we first solved for R1 by summing up moment about 2, R2 equals 0. So clockwise is positive. So we have R1 times L equals P1 times B plus C plus P2 times C. But because this value here is the same as this right side of equation 1, which we denoted earlier as summation moment about T due to the loads, and this is supposedly summation moment about T due to the loads. So R1 times L equals summation moment about T due to the loads. Then, knowing R1, we can now compute the moment at Q, which is to cut the beam at this section containing Q, then the moment at Q is R1 times X, then minus P1 times X minus A, minus P2 times quantity X minus quantity A plus B, which is the same here if you transpose to the right. So R1 is equal to summation moment about T due to the loads divided by L. Let's call that equation 4. So MQ therefore is R1 times X, because the distance of Q from the left is X, same as above, minus P1 times X minus A, then supposedly minus P2 times quantity X minus quantity A plus B, or simply minus quantity P1 times X minus A plus P2 times quantity X minus quantity A plus B. And take note that this expression is equal to summation of moment about point Q due to the loads, which is the same as that. So MQ therefore equals R1 times X minus summation moment about Q due to the loads. So substituting the value of R1, so from this equation, by the way, V sub A is equal to H, divide everything by L from equation 1, so H tangent theta, then plus summation of moment about D due to the loads divided by L. So this equation comes from this equation 1 here. Then after we divide by L and transpose this part to the right, then substitute this equation into equation 3. So into equation 3, and take note that equation 3 from here. So we have H tangent theta plus summation moment about D due to the loads over L times X minus H times quantity HQ plus X tangent theta equals summation moment about Q due to the loads. So if we simplify this, take note that we can eliminate H tangent theta because there is negative HX tangent theta, then we have also negative HX tangent theta. So that is eliminated. Then what would be left is summation moment T due to the loads times X over L, then minus H sub Q equals summation moment Q due to the loads. So summation moment T due to the loads over L times X minus H times H sub Q equals summation moment about point Q due to the loads. So substituting from this equation the value of MQ, which is R1X minus summation moment. So by the way, this from this equation here, we have R1X minus HQ equals summation moment about Q due to the loads, because R1 is summation moment about D due to the loads divided by L. So we interpret this expression as simply R1. Then we have X, this is R1 from this equation here, and times X minus H, capital H times H sub Q equals summation moment about Q due to the loads. So since R1X from this expression here is actually R1X minus this equals HHQ. So we interpret R1X minus emission moment about Q due to the loads as MQ. Then that is equal to HHQ. So R1X minus emission moment about point Q due to the loads equals HHQ. We transpose this to the right, transpose this term to the left. So that's the expression. And take note from equation 5, we interpreted this as MQ. So therefore, we have verified the theorem that it is correct. So MQ equals H times H sub Q. That's the general. Then cable subjected to, let's continue, vertical uniform loads over a horizontal span. So what if the beam is subjected to horizontal load, vertical uniform loads, then projected on a horizontal span, like this one. So this is a symmetrical cable, and we will show here that the equation of this cable is a parabola. So take note of the elements. So the slope at A is theta A. The tension, of course, is T sub A. This is the y-axis. That's the x-axis. So the lowest point on the cable is the origin. The vertical distance of point O from the imaginary chord, which is in this case horizontal because it is symmetrical, is denoted by D, which is the sag. Then we have theta B, which is equal to theta A because it is symmetrical. The length of the cable from point A, from the left to O, is denoted by S, and from O to B is also S by symmetry. Then we draw the free body diagram. So that's the horizontal component of tension. It's the same. The vertical component of tension is simply WL over 2 by symmetry. So if you cut up to O, then of course the area of this left portion of the load is simply the area of the rectangle W times L over 2. That's why VA is, vertical component is WL over 2. So we then draw the free body diagram of the portion of this cable here from O to any point on the cable, P, not D, so somewhere here. And the length of the horizontal projection is X because this is rectangular load. Then the centroid is, of course, at X over 2 from either left or right end of that portion. Because this is the lowest point, the tension there is simply H. There's no vertical component. The tangent is horizontal. And therefore, this is also H. Then the vertical component of force here is W times X, which is the area of the rectangle. Summation moment about P equals 0, clockwise positive. So we have H times Y. Of course, this is Y. Equals Wx times x over 2. So y equals Wx squared over 2h, which represents parabola. It is a second degree equation. So from here, this equation tells us that the cable is a parabola or parabolic. Then that's Wx. So let's draw the first triangle here. We have Wx, then H, then T. And the angle here is theta. So that we can now set up the general formula for the tension. It is simply square root of H squared plus quantity Wx quantity squared. So you don't need to memorize that. As long as you just draw this free body diagram, you can easily remember that. Then also tangent theta is Wx over H. So that's the slope at any point on the cable. Then for symmetrical cables, then you simply replace X by L over 2. Then you can solve for the tension if it is symmetrical cable, tension at A or tension at B. And this is also the general formula for the tension. So TA equals T sub B for symmetrical cable, H square plus WL over 2 quantity square. So you don't need to memorize that. Just this general equation from this force triangle. Tangent theta also is equal to tangent theta A, tangent theta B. It is equal to replace X by L over 2, so WL over 2H. For that case, you don't need to memorize that. Because at D, X is L over 2, this is the origin, and Y is equal to D, of course, the sag. Substitute it into this equation, the parabola. D equals W times L over 2 quantity square over 2H. So that's why we have HD equals WL square over 8. If you're going to interpret this result, remember the general cable theorem. If we imagine a beam here loaded with this uniform load, remember that the maximum moment occurs at the center of the beam, and it is equal to WL square over 8. And actually, this is the application of the general cable theorem. Remember, the general cable theorem states that the product of the horizontal component of tension and the vertical distance of any point on the cable, in this case point O from the imaginary chord, which is D, is equal to the moment at the same point, which is O, or the center of the beam, loaded with the same loading, which is uniform load W. So I hope that you know that the maximum moment in a beam, simply supported beam, symmetrical beam loaded with uniform load across the entire span, is WL square over 8. So that's it. Actually, this is the general cable theorem. So I hope you won't find trouble in remembering this relationship. So the formula for H is WL square over 8D. So H is WL square over 8D. That's the formula. And if you mind, that's constant here. So meaning the maximum tension occurs at the highest point. Why at the highest point? Because at the highest point, X is maximum. So if you want to maximize the tension, then it should be far or farthest from the origin. So that's the location of maximum tension. And maximum slope also occurs at the highest point. So this is the horizontal component of tension, which is also the tension at the lowest point. So take note that that horizontal component of tension is any point on the cable. The horizontal component is H. If you draw the free body diagram, that should always be H, as long as the load is vertical, meaning to say there's no inclined load or concentrated load. So this is for symmetrical cable only, and you will learn from the examples that these equations can also be applied to unsymmetrical cables. But actually, all parabolic cables are symmetrical with respect to its axis. So even if the supports are not at the same level, then you can always draw a horizontal line to isolate a symmetrical portion of the cable. So y equals wx square over 8 over 2h, and h is wl square over 8d. So the equation of the cable is y equals 4d over l square then times x square. So 4d over l square times x square. This is the equation of the parabolic cable. Symmetrical parabolic cable. So for the length of entire cable, then S is, so we have to consider a slope here, tangent theta, then the components would be dx and dy, and the hypotenuse would be differential S. So this is from calculus, integral calculus specifically. So we will derive the formula for S. So differential S square by Pythagoras equals dx square plus dy square, or ds is square root of dx squared plus dy squared. We can multiply everything by 1, and 1 is represented by dx over dx. Insert the denominator dx into the radical, so it becomes square. So dx squared over dx squared is 1, and this is dy dx quantity square or slope square. So ds is square root of 1 plus dy dx quantity square dx after we insert this denominator into the radical. So integrating s therefore is the integral from 0 to L over 2 of 1 plus dy dx squared dx, 0 to L over 2. And if the high-tech calculator is allowed, then you will find easy supposedly. But because the high-tech calculator is not allowed, then we will proceed by deriving the exact formula and the approximate formula for the length of the cable. So the total length is just you double this length. So 2s equals 2 integral 0 to L over 2 square root of 1 plus dy dx quantity square dx. That's the expression for the total length of cable. So for symmetrical cable only. So y is 4d over L square. Let's derive dy dx. So if you differentiate, then dy dx is 8d over L squared times x. So dy dx is 8d over L squared times x because the derivative of x squared is 2x. So s total equals 2s equals 2 integral 0 to L over 2 1 plus dy dx quantity squared dx. So replacing dy dx by 8d over L squared times x, so quantity squared dx. And this is familiar from integral calculus when the integrand involves constant square, 1 square plus variable square. You put the variable equal to constant tangent of theta. You can remember. So by binomial expansion theorem, let's have the approximate formula first. We have the binomial expansion theorem from algebra, that first term plus second term quantity to the n is equal to first term raised to n divided by 0 factorial plus n times first term to the n minus 1 times second term divided by 1 factorial. This is supposed to be 1 factorial. Then plus n times n minus 1 f to the n minus 2 s squared over 2 factorial plus n minus 1 n minus 2 f n minus 3 s cubed over 3 factorial and so on and so forth. I hope that you encounter this in your algebra time. So that's really the expression. So to help you explain this expansion, supposedly this is not algebra. So it is first term raised to n divided by 0 factorial because the power of s in the first term is 0. So you divide everything by 0 factorial. Anyway, 0 factorial is equal to 1. Then it's like differentiating f. So n f to the n minus 1, right? The derivative supposedly. Then we subtracted the power of f, which is supposedly n. Then we subtracted 1. Whatever is the power subtracted from the power of the first term, that's also the power of the second term, which is s to the 1. Then whatever is the power of the second term, you divide the entire term by the factorial of that power. So 1 factorial. 1 factorial is also 1, of course. Then here, n, the derivative of f times n minus 1 is n times power n minus 1 f to the n minus 2. So that's why it appears here. Then since we subtracted 2, then the power of the second term s is also 2. The entire term is divided by the power of the second term factorial. Then plus n times n minus 1, the derivative of f to the n minus 2 is n minus 2, f to the n minus 3. Then because we subtracted 3, the power of the second term would now be 3 also, divided by 3 factorial, and so on and so forth. Now, we ignore the succeeding terms because when the power is less than 1, in this case 1 half, because this is 1 plus, this is the first term 1, this is the second term square, but the entire power, the value of n is 1 half, which is less than 1, then the succeeding terms will be negligible. So simplifying, the first term is f to the n, the second term is, so this is the original binomial, so n is 1 half, so substitute the value of n here and the value of the second term. Because the first term is 1, the second term is 8b over L squared times x, and n is 1 half. So S total equals 2 times integral 0 to L over 2. So f to the n is, first term is 1, so 1 to the 1 half over 1, which is 1, plus n, which is 1 half, divided by 1, it's still 1 half. And first term to the power 1 half minus 1 is negative 1 half. So 1 to the negative 1 half is still 1. Then the second term appears, which is 8d over L squared. 8dx, this is not differential of x. 8d times x over L squared, quantity squared. That's the second term. Then plus 1 half. 1 half minus 1 is negative 1 half. Then first term is 1 to the 1 half minus 2 is negative 3 halves. Second term raised to 2, since the second term is 8dx over L squared square. So raised to 2, so it becomes raised to 4. Then divided by 2 factorial is still 2. Then this fourth term here is 1 half times negative 1 half times negative 3 halves times 1 to the negative 5 halves. Then second term square raised to 3 is second term raised to 6 divided by 3 factorial, which is 3 times 2 times 1, so it is 6. And plus dot 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 times differential of x. So simplifying the terms inside these brackets, we have st equals 2 integral 0 to L over 2 of 1. Then the second term is 32 over L to the fourth d square x square, then minus 512. We just simplify, evaluate the numerical values of the coefficient. 512 d to the fourth x to the fourth over L to the fourth, L to the 8th rather, then plus 16 384 d to the 6 x to the 6 over L to the 12, plus and so on and so forth. So of course the integral of 1 is x, 0 to L over 2 is L over 2. Integral of this term, don't mind constant, you just copy that, x cubed over 3. And this is minus 512 d to the 4th over L to the 8 x to the 5 over 5. Then 16 384 d to the 6 over L to the 12 x to the 7 over 7. So S total is equal to x plus 32 over 32 d squared over 3 L to the 4th, x cubed. So supposedly x cubed over 3, so this is the 3, minus 512 d to the 4th over L to the 8th. Then the integral of x to the 4th is x to the 5 over 5. So that's it. Then plus 16 384 d to the 6 over L to the 12. Integral of x to the 6 is x to the 7 over 7. Limits 0 to L over 2. So substitute. So lower limit would just be 0, L over 2 plus 34 d squared over 3L, because this is L over 2 cubed, so 1/8, L cubed over 8, so cancel L cubed, so we have L here. And minus 16 d to the 4th over 5L cubed, because 512 is divided by 32. L over 2 to the 5 is L to the 5 over 32. So it reduces to that 16. but 5 is still there, then plus 128 over 7 d to the 6 over L to the 5. So if we distribute 2 and factor out L, so we have S total equals L plus 8 thirds d squared over L minus 32 over 5 d to the 4th over L. We distributed 2 here. Then factor out L. So you have S total is L quantity 1 plus 8 thirds d squared over L squared minus 32 d to the 4th over 5 L to the 4th, then plus 256 d to the 6 over 7 L to the 6. So this is the approximate formula for the total length of the cable. And to easily recall it or memorize it, we replace D over L as K so that we can reduce it to length total equals L quantity 1 plus 8 thirds K squared minus 32 over 5 K to the 4th plus 256 over 7 K to the 6, where D over L is denoted by K. So these are the two approximate formulas for the length of the cable. And you can use this because the high-tech calculator is no longer allowed. So if I were you, you familiar the second one. Actually, you will notice that the fourth term is very, very small. So you can memorize just the first three if you want, but if you want the more accurate length, then include the fourth term. Approximate length of symmetrical parabolic cable. So let's now move on to derive the exact formula for computing the length of the cable. So let's go back to the original expression, 2 integral 0 to L over 2 of square root of 1 plus 8b over L square x squared dx. Then we put the variable, which is 8b over L square x, as u equals a tangent theta, and a is 1, remember? Then differentiating with respect to x, so 8b over L squared dx is derivative of tangent is secant squared theta times differential of theta. But before that, let's define in this right triangle tangent of theta, which is opposite 8b over L squared x divided by adjacent, which is 1. That's theta, so this should be 8b over L squared x from tangent theta equals opposite over adjacent 1. So the hypotenuse should be equal to the square root of 1 plus quantity 8b over L squared x quantity squared, which is in terms of 1 and theta, it is simply 1 times secant theta, or simply secant of theta. So 8b over L squared dx equals secant square of theta d theta from the derivative of differential of this equation here. So dx therefore is L squared over 8b times secant squared theta d theta. So that in this expression, total length is 2, integral from 0 to L over 2, square root of 1 plus 8b over L squared x quantity square is secant theta, while differential of x is L squared over 8b secant squared theta. This is differential of x from this equation here. So putting all the constants before the integral sign, and you have L squared over 4d integral of secant cube theta differential theta. I will not put the limits here because we change variables from x to theta. And from calculus, the integral of secant cube theta d theta, this is an example problem from Love and Rainville book in calculus. But if you can remember the integral of secant cube theta d theta, then there is no problem. So the integral of secant cube theta d theta is actually 1/2 of quantity secant theta tangent theta plus ln of quantity secant theta plus tangent theta. That is if you remember that integral. So 1/2 of quantity secant theta plus tangent theta plus ln of secant theta plus tangent theta. So simplify and replace secant theta and tangent theta from this triangle here. So S total equals L square over 8D. Quantity secant theta is square root of 1 plus quantity 8D over L square x square over 1. So it's still square root of 1 plus 8D over L square x quantity square. While tangent theta is opposite over adjacent, because adjacent is 1, so it is just opposite. And plus ln, so we simply copy these terms but break into plus into two terms. So limits are now enforced because we change the variables back to the original. So 0 to L over 2 for symmetrical cable. So that's why we multiply the entire length by 2, because we apply this for symmetrical cables. Then when x is 0, lower limit, let's show that it is just 0. So the whole of this is square root of 1, but there is x here 0, so the entire first term of the integral is 0. Then in this second term, this is 0, and this is 0, so we have ln of square root of 1. Square root ln of 1 is, so ln of square root of 1 or ln of 1, because ln of 1 is 0, so when we substitute the lower limit, everything will be 0. So we are only concerned of the upper limits, which is L over 2. So if x is L over 2, the simplified term inside this parenthesis would be 4D over L. So 4D over L, this is 4D over L, this is 4D over L, this is 4D over L. So S total is L squared over 8D, quantity square root of 1 plus, so let us substitute the actual value of upper limit first and observe that it is just 4D over L. You simplify and minus 0 lower limit. So S total equals L squared over 8D, quantity square root of 1 plus quantity 4D over L quantity square plus times 4D over L plus ln of quantity square root of 1 plus 4D over L square plus 4D over L. Then ln. So since 4D over L appears in each term, you can let that equal to m. So L squared over 2 times 4D over L also. Let's break this into this form. And square root of 1 plus 4D over L squared, 4D over L plus ln of square root of 1 plus 4D over L quantity squared plus 4D over L. So replacing 4D over L by m, so let m be 4D over L, then total length is S total equals L over 2m, quantity square root, quantity m square root of 1 plus m squared plus ln of quantity m plus square root of 1 plus m squared. So it's easy to memorize, especially if you derive this also. And remember that m is 4D over L. So the total length is L over 2m for symmetrical cable, quantity m plus square root of 1 plus m squared plus ln of m plus square root of 1 plus m squared. Actually, all you have to do is familiar with these terms here, m and square root of 1 plus m squared, then break them into two parts, then it is ln. So ln of m plus square root of 1 plus m squared. That's my technique in memorizing this formula, exact formula for the length of symmetrical parabolic cable. So that's it for the length of symmetrical parabolic cable. On, let's now have the theory on catenary cables. So it sags due to its own weight. There's no other load except its own weight. So this is the configuration. So we have the uniform weight of the cable, and it is subjected along the length of the cable because it is uh, subjected along the, or it is the weight of the cable itself. So it's no longer rectangular, so it's a bit uh, complicated, but actually it's simple if you are good in calculus. So these are the elements. We have the length of the cable, which is not that entire length. So we break this into S and S, theta A, theta B for symmetrical catenary. Then the theta A and theta B will be equal, and the tensions are also equal. So take note that the x-axis is now below the lowest point on the cable, and the y-axis remains the same. And the distance from the lowest point of the cable to the x-axis is c, and c is defined as the ratio of the horizontal component of tension, which is constant still because these are all vertical loads, divided by the uniform weight of the cable. So that's the origin. So c is defined as the ratio of the horizontal component of tension and the uniform weight of the cable. And what is new here is the origin is no longer at the lowest point of the cable, just like in parabolic cable. The origin was at the lowest point, but here it is below the lowest point, and the distance is c, which is defined by the ratio of the horizontal component of tension and divided by the uniform weight of the cable. So as before, we consider portion of the cable from the lowest point to any point here, let us say P, and the slope in general is theta also. Then the distance, horizontal distance is x. Then the distance of O from the distance of the lowest point from the origin is C. That's WS. WS, where S is this, the small letter S is this. So just like before, we consider tangent at point P. So the elements are dx, dy, and ds. So that's it. So first triangle, we have ws, then h to the left, then tension, which is equal to t. And this angle here is theta. So tension is square root of h squared plus ws quantity squared. So what is new here is that from parabolic cable it was wx, this time it's ws, the vertical component of tension from the lowest point to any point. So replacing h by wc, because h, capital H is wc from the figure. Tangent theta, by the way, is ws over h, and replacing h by wc, that's the slope at any point. That is y, that's x. So let's call that yb. So tension is wc quantity square plus ws quantity square. W square is common. Square root of w square is w, so you can put w before the radical and write it tension equals w times square root of c square plus s square. And the slope, tangent theta, which is dy dx from calculus, is ws over wc. So we can cancel w. Tangent theta, which is dy dx, is equal to s over c. So let's begin with this equation. ds is square root of dx squared plus dy squared times dx over dx. Again, just like before, put dx, the denominator dx, into the radical, so it becomes dx squared into the radical. So dx squared over dx squared is 1. Then dy dx quantity squared times dx. So ds over dx is square root of 1 plus dy dx quantity squared. And dy dx is actually the slope of the tangent to the cable, to the curve. And dy dx is tangent of theta from calculus. So it is s over c. So ds dx equals square root of 1 plus s over c quantity squared. Then simplifying, ds dx equals square root is 1 over c square root of c squared plus s squared. We can separate the variables. So s, because s is c tangent theta, so differential of s is c secant squared theta d theta. So we define another triangle here for tangent. So this is theta. Tangent theta is opposite s adjacent c. So the hypotenuse is square root of c squared plus s squared, which is c secant of theta. Square root of c squared plus s squared is c secant theta. So into this equation here, ds is c secant squared theta, and we cross multiply here, so we have 1 over c square root of c squared plus s squared times ds. Cancel out c. Oh, uh, so c secant squared theta d theta equals c secant theta dx over c, because this radical here, square root of c squared plus s squared, is c secant theta divided by c. So we can cancel c here, and we can cancel secant theta. So dx is c secant theta d theta. So dx is c secant theta. Of course, there is d theta. So x is therefore integral of c secant theta d theta. From calculus again, the integral of secant theta is ln of quantity secant theta plus tangent theta. And we have here the constant of integration, k1. So to evaluate k1, when x is 0, y is c. Y is not 0 because the origin is here. Y is c. And we can show that k1 is 0 also. So we have x is equal to c ln of secant theta. From this triangle, secant theta is hypotenuse, which is square root of c squared plus s squared divided by adjacent c, and tangent theta is s over c, which is a given, plus k1. So when x is 0, s is 0, and let's show that k1 is 0. So x0, y is c, and s is 0, so that when x is 0, and you have c ln of, because s is 0, so we have square root of c squared over c, which is 1, and this is 0, so ln of 1 is 0, so that k1 is 0. So we have x is therefore equal to c ln of square root of c squared plus s squared over c plus s over c, which can be simplified further into x over c equals ln of square root of c squared plus s squared plus s all over c. So the formula for x is c, so square root of c squared plus s squared plus s over c is equal to, convert this equation, so this is ln, so meaning to say e to the x over c is equal to square root of c squared plus s squared plus s over c. So remember, if you have y equals ln of x, then if you want to solve for x, it is e to the y. So just like this. So this expression here is equal to e to the x over c. Then cross multiply, square root of c squared plus s squared plus s equals c e to the x over c. Transpose s to the right. So square root of c squared plus s squared equals c e to the x over c minus s. Square both sides. So we have c squared plus s squared equals c squared e to the 2x over c minus 2cs e to the x over c plus s squared. So we can cancel out s squared. So write it as c squared equals c squared e to the 2x over c plus minus 2cs e to the x over c. Transpose this negative 2cs e to the x over c, but before that, divide everything by c, transpose also c squared to the right. So we have 2s e to the x over c equals c e to the 2x over c minus c after we divide everything by c and simplify. So finally, we can now set up the formula for s by dividing this right side by 2 e to the x over c. So 2s e to the x over c equals factor out c, so e to the 2x over c minus 1. Divide everything by 2 e to the x over c, so s equals c over 2 times quantity e to the x over c minus e to the negative x over c. So of course 2x over c divided by e to the x over c is e to the x over c, and minus 1 divided by e to the x over c is negative e to the negative x over c. And I hope you can familiar this equation here from calculus. If you have 1/2 of e to the u minus e to the negative u, that's actually sine hyperbolic of u from calculus. So cosine hyperbolic of u is 1/2 of e to the u plus e to the negative u. Sine hyperbolic of u is 1/2 quantity e to the u minus e to the negative u. And tangent hyperbolic of u is e to the u minus e to the negative u all over e to the u plus e to the negative u. And remember also the identity that cosine hyperbolic square of u minus sine hyperbolic square of u equals 1. To verify this identity, you have to substitute this cosine equivalent, then square it, minus the square of this term, you will get 1. So that's why that's the identity. You can divide by cosine hyperbolic square and write it as 1 minus tangent hyperbolic square of u equals secant hyperbolic square of u. You can divide everything by sine hyperbolic square, so you have cotangent hyperbolic square of u minus 1 equals cosecant hyperbolic square of u. But I just leave that to you. These are the important equations. So that we write this as s equals c, and this is sine hyperbolic of x over c. So s equals c sine hyperbolic of x over c, because u is x over c in that case. So that's the formula for s. Not the entire length, but just a portion from the lowest point on the cable to any point. So derivative of y with respect to s is s over c. So because we have derived s, 1 over c, s is c sine hyperbolic of x over c. So dy dx is sine hyperbolic of x over c, or dy equals c sine hyperbolic of x over c dx. But because we want to derive the equation of the catenary, so you have here dy equals c sine hyperbolic of x over c, and we put this c here as into denominator of differential of x, so that this is in the form sine hyperbolic of u. The differential of x over c is 1 over c differential of x, or dx over c, so that you can imagine that the right side is sine hyperbolic of u differential of u, And of course, we can easily evaluate the integral because the integral of sine hyperbolic of u is simply cosine hyperbolic of u. So in this case, y equals c cosine hyperbolic of u, and u is x over c plus the constant k2. Then let's show that k2 is 0 because when x is 0, y is c. So this is c equals c cosine hyperbolic of 0. Cosine hyperbolic of 0 is 1. So c minus c is 0, so k2 is 0. So therefore, the equation of the catenary is y equals c cosine hyperbolic of x over c. That's the equation of the catenary. So remember the identity, cosine hyperbolic square of u minus sine hyperbolic square of u equals 1 because we already derived the equation of the catenary, y equals cosine hyperbolic of x over c. So we have cosine hyperbolic square of x over c minus sine hyperbolic square of x over c equals 1. And this is simply y over c. The first term is y over c quantity square. The second term is s over c quantity square equals 1. Or y squared minus s squared equals c squared. Or simply y squared equals c squared plus s squared. So remember of the tension at any point on the cable, W times square root of c squared plus s squared. So this square root of c squared plus s squared is simply square root of y squared, which is y. So the tension is simply W times y. So that's the reason why the tension at the lowest point is W times C. Remember, capital H equals W times C because the distance of the lowest point on the cable from the origin is C. So if you have a point on the cable and its distance from the x-axis is y, so the tension at that point on the cable is simply W times y. Which is easy to remember because it's just the product of the uniform weight of the cable and its vertical distance from the x-axis. So let's summarize the formulas for catenaries. So we have tension equals square root of h squared plus quantity ws squared, which can be at any point, or simply replacing h by wc. So it's w squared of c squared plus s squared, and it reduces to w times y. Tangent theta is s over c, or ws over h, the original, but h is w times c, so it reduces to s over c, and that is the slope of the tangent to any point on the cable, which is from calculus dy dx. Then y is c cosine hyperbolic of x over c, s is c sine hyperbolic of x over c, x is c ln of square root of c squared plus s squared over plus s over c, s is c sine hyperbolic of x over c, y is c cosine hyperbolic of x over c. So that's all.